The acoustic cooled ceiling panel from Rayhow is an interesting new product. It's actually our first installation in North America. We're installing it here at the EcoSmart house in Bozeman, Montana. And we're going to be able to monitor the way that this panel is able to cool the space effectively while also absorbing unwanted noise within the space, as it has both cooling capacity and acoustic properties built into the panel. The Rayhow acoustic cooled ceiling panel is composed of two approximately 3/8 inch gypsum boards which have been pre-routed to receive a 10mm PEX pipe. This PEX pipe is then serpentined throughout the panel in order to create an even cooled surface. On the bottom surface of this panel are perforations which do not just increase the amount of cooling capacity but also serve to increase the sound absorbing character of the panel itself. This is a really unique application to use for cooling in that you're able to allow the warm air to rise within the room and then effectively absorb it directly with the panel and remove the heat from the space via the PEX tubing. Each one of these panels is ganged together in forming 5 total circuits, so 3 will form together with approximately 60 meters of tubing, and then they will go back to the manifold and be serviced by a single supply and return line. Each circuit also has individual capabilities to be monitored and turned on and balanced as needed. The capacity for heating and cooling is also available from these acoustic cooled ceiling panels. Being a new technology in North America, this is our first pilot installation of the acoustic cooled ceiling panel, and we will be using it to monitor the way that it interacts with our other radiant cooling systems, such as the radiant cooling in the slab below our feet, as well as the eco-air and geothermal applications that are also involved with the project. One of the unique things about Bozeman, Montana is its climate is perfectly suited for the acoustic cooled ceiling panel. In the application here, there are relatively high heating loads and relatively low cooling loads, which can actually be 100% supported by the acoustic cooled ceiling panel in this area. We're able to effectively absorb all the BTUs required in order to fully condition the space at any time of the year. Rayhow's ProBalance manifold is connected up to the panels in such a way that it creates 5 circuits. Each of these circuits is made up of 3 panels which are ganged together, forming a total of 15 radiant cooling panels that are used in the application. So what we have on the installation is we have 3 chilled ceiling elements that are going to go into the structure of the ceiling. And the 3 of them will be ganged together to create one circuit, approximately 60 meters or about 180 feet. And that's then going to be connected to a supply and return line that's going to go back to the mechanical room and connect up to our Rayhow ProBalance manifold in order to supply and distribute both warm water as well as cooled water in the cooling season.
My name is Daniel Rhodes. I am a student for Montana State University, working for the Montana EcoSmart House project, sponsored by Rayhow. This is the data acquisition system that we've designed to monitor the sensors that have been placed within the EcoSmart House. These sensors will monitor the performance of the house and its technology so that the average consumer can go on and see how these new products and technologies perform. This is the SCXI 1001 data acquisition system by National Instruments. This is the chassis that will be used to hold all the sensor components that will be monitoring the house. And how it works is all the sensors come into these terminal blocks, which compose of 4 thermocouple specific terminal blocks, as well as 2 other terminal blocks that will monitor other non-thermocouple signals. And how those function is the thermocouple wires will come in and plug directly into those, and they come up from here and are plugged into these terminal block connectors. And these are how the sensor wire that is in the house is brought in and then changed over to this smaller, more compact wire. So each of your signals comes in, is routed through here and back into the system. There's also terminal blocks for non-thermocouple signals, as well as a pulse counter converter to transform signals that are in hertz, such as a flow meter for how fast water is flowing through tubing, into a usable signal from the DAC system. These are an example of the sensors placed within the house. This is a bundle of 4 T-type thermocouples that have been placed within the Anvic ICF concrete forms. Each one of these is on each different layer of the concrete forms and measure the temperature at that layer. How these work is 2 different metals, when touched together, cause a voltage drop that varies depending on temperature, and their response time is so quick that I can just touch my fingers to it and there's an immediate spike in temperature shown on the graphs. And as these temperatures change, it is calculated into a rate of heat transfer through the walls that will help monitor the wall's performance.
So we have 120 feet of 4-pair thermocouple wire, which is just 4 individually wrapped thermocouples all in one wrapping. So the first step, I have to unsheath the wrapping. So I'm just simply that I'm going to do. I have to separate, because there's 4 thermocouples in this bundle, I have to separate the red wire labeled 1 with the blue wire labeled 1 and continue on with the red wire labeled 2 and the blue wire labeled 2, etc. up through 4. And then I will strip those back about 2 inches down to the copper wire, or the copper and nickel wire, and then weld them into thermocouple tips. So we will have our 4 temperature sensing devices. So this is a 4-pair thermocouple wire, and what it is, it looks like it's just one wire, but it's actually 4 individual thermocouples. And these are each labeled 1 through 4, so we can keep track of which thermocouple on the end that is going to be hooked up to the computer. We can keep track of which thermocouple is which. And this specific thermocouple is going to be used to measure the temperature through the heat sink. And the heat sink serves to get rid of excess heat from the solar thermal system during summer when you're not using all of that extra heat. And so the next step for this is to strip the wire down to the nickel and copper, and then we can weld it in our thermocouple welder to sense the temperature via voltage. So now I'm stripping the insulation off the wire in order to clear the actual metal so we can weld these 2 ends together. So the next thing I will do is turn on the check valve in order to allow the gas to flow to the welder. So now insert the tip with about 1 centimeter of wire shown from each wire in order to weld the 2 tips together. Now, as you can see, it successfully welded the 2 tips via electric weld. Now you can see that all 4 thermocouples in the thermal pair have been welded and they are ready to sense temperature. The next step, now that the thermocouples are welded, is to encase these using rubber cement to prevent corrosion in the future. So the first layer of rubber cement is done. We will let this dry and then we'll put a second coat on. And then the final coat, to prevent corrosion, we will wrap it in duct tape. So here's our thermocouple welding setup, and this is the actual thermocouple welding unit that uses electricity to weld the thermocouples. And this is our argon shielding gas, which removes many of the atmospheric contaminants, which can reduce the strength of a typical weld. So this is our data acquisition setup, and these 4 terminal blocks right here will be our inputs for all our temperature sensors throughout the house. And these 2 modules right here can have a greater range of voltages that they can accept. So our flow meters and various other sensor types will input into these terminal blocks. And this data acquisition unit will then feed to the computer, where we will have a program that monitors all these signals and processes them.